Welcome to the fascinating world of quantum physics. In this video, we'll embark on a journey to explore the mysterious and often counterintuitive rules that govern the smallest particles in our universe. Quantum physics challenges our everyday understanding of reality, introducing concepts that seem almost magical. From the dual nature of light to the strange behavior of electrons, quantum physics has revolutionized science and technology. Whether you're a curious beginner or someone looking to deepen your knowledge, this series will guide you through the core ideas, experiments, and real-world applications of quantum mechanics. Let's dive in and unravel the secrets of the quantum world together. Quantum physics, also known as quantum mechanics, is the branch of science that studies the behavior of matter and energy at the smallest scales, typically at the level of atoms and subatomic particles. Unlike classical physics, which explains the motion of everyday objects, quantum physics deals with phenomena that defy our common sense. For example, particles can exist in multiple states at once, and their properties can change simply by being observed. This field has not only transformed our understanding of the universe, but also paved the way for groundbreaking technologies like lasers, transistors, and quantum computers. Origins of quantum physics date back to the early 20th century, when scientists began to notice that classical physics couldn't explain certain phenomena, like the way light emitted from heated objects. Max Planck introduced the idea that energy is quantized, meaning it comes in discrete packets called quanta. This revolutionary concept laid the foundation for quantum theory. Soon after, Albert Einstein used quantum ideas to explain the photoelectric effect, showing that light itself behaves as both a wave and a particle. These discoveries marked the beginning of a new era in physics. One of the most mind-bending aspects of quantum physics is wave-particle duality. This principle states that particles such as electrons and photons can behave both as particles and as waves depending on how they are observed. The famous double-slit experiment demonstrated this duality. When not observed, particles create an interference pattern like waves, but when measured, they act like individual particles. This strange behavior challenges our classical intuition and lies at the heart of quantum mechanics. Werner Heisenberg introduced the uncertainty principle, a cornerstone of quantum physics. It states that it's impossible to know both the exact position and momentum of a particle at the same time. The more precisely we know one, the less precisely we can know the other. This isn't just a limitation of our measuring tools, it's a fundamental property of nature. The uncertainty principle has profound implications for how we understand reality at the quantum level, showing that the universe is inherently unpredictable on small scales. Quantum superposition is another fascinating concept. It means that a quantum system, like an electron, can exist in multiple states at once until it is measured. For example, an electron can be in two places at the same time, or a photon can have two different polarizations simultaneously. This idea is famously illustrated by Schrödinger's cat thought experiment, where a cat in a box can be both alive and dead until someone looks inside. Superposition is essential for technologies like quantum computing. Quantum entanglement is one of the most mysterious and intriguing phenomena in quantum physics. When two particles become entangled, their properties become linked, no matter how far apart they are. If you measure one particle, you instantly know the state of the other, even if it's on the other side of the universe. Einstein famously called this spooky action at a distance. Entanglement has been confirmed by experiments and is the basis for emerging technologies like quantum cryptography and teleportation. Double-slit experiment is a classic demonstration of quantum weirdness. When particles like electrons are fired at a barrier with two slits, they create an interference pattern on a screen behind as if they were waves passing through both slits at once. However, if you try to observe which slit the particle goes through, the interference pattern disappears and the particles behave like individual particles. This experiment highlights the role of observation in quantum mechanics and the strange duality of matter. Quantum tunneling is a phenomenon where particles can pass through barriers that would be impossible according to classical physics. Imagine a ball rolling up a hill that doesn't have enough energy to get over the top. In the quantum world, there's a chance the ball will simply appear on the other side as if it tunneled through the hill. This effect is crucial in many technologies, such as the operation of tunnel diodes and the nuclear fusion that powers the sun. Quantum physics outcomes are described by probabilities rather than certainties. Instead of predicting exactly where a particle will be, quantum mechanics gives us the likelihood of finding it in a particular place. This probabilistic nature is described by the wave function, a mathematical tool that encodes all possible states of a system. When we make a measurement, the wave function collapses to a definite outcome. This shift from certainty to probability marks a major departure from classical physics. Wave function is a central concept in quantum mechanics. It's a mathematical description that contains all the information about a quantum system. The square of the wave function gives the probability of finding a particle in a particular location. The wave function evolves over time according to the Schrödinger equation, another cornerstone of quantum theory. Understanding the wave function is key to grasping how quantum systems behave and interact. Schrödinger's cat is a famous thought experiment that illustrates the paradoxes of quantum superposition. Imagine a cat in a sealed box with a device that has a 50% chance of killing the cat, depending on the state of a quantum particle. Until you open the box and check, the cat is both alive and dead at the same time. This scenario highlights the strange consequences of quantum mechanics and the role of observation in determining reality. Measurement in quantum physics is a complex and subtle process. When we measure a quantum system, we force it to choose a definite state from among all its possible states. This is known as the collapse of the wave function. The act of measurement itself influences the outcome, which is very different from how things work in classical physics. Understanding quantum measurement is essential for interpreting experiments and for developing quantum technology. Spin is a unique quantum property of particles like electrons and protons. Unlike spinning objects in our everyday world, quantum spin doesn't refer to physical rotation. Instead, it's an intrinsic property that gives particles their magnetic characteristics. Spin can only take certain values, such as up or down, and plays a crucial role in the behavior of atoms and the structure of matter. Spin is also fundamental to technologies like magnetic resonance imaging, MR. Pauli exclusion principle, formulated by Wolfgang Pauli, states that no two identical fermions, such as electrons, can occupy the same quantum state at the same time. This principle explains the structure of the periodic table and why matter takes up space. It's the reason why electrons fill different energy levels in atoms, and why stars like white dwarfs and neutron stars are stable. The Pauli exclusion principle is fundamental to the stability of matter in the universe. Quantum numbers are used to describe the properties of electrons in atoms. Each electron is characterized by a set of quantum numbers that specify its energy, angular momentum, and spin. These numbers determine how electrons are arranged in atoms and how they interact with each other. Understanding quantum numbers is essential for explaining the chemical behavior of elements and the structure of the periodic table. Quantum physics, electrons in atoms can only occupy certain energy levels. When an electron absorbs energy, it jumps to a higher level. When it releases energy, it falls back down, emitting light in the process. These discrete energy levels explain the unique spectra of elements and are the basis for technologies like lasers and fluorescent lights. The concept of quantized energy levels is one of the key differences between classical and quantum physics. Quantum field theory extends quantum mechanics to fields, such as the electromagnetic field. In this framework, particles are seen as excitations of underlying fields that fill all of space. For example, photons are excitations of the electromagnetic field. Quantum field theory is the foundation of the Standard Model of particle physics, which describes all known fundamental particles and forces except gravity. Standard Model is the most successful theory of particle physics to date. It describes 3 of the 4 fundamental forces, electromagnetic, weak, and strong interactions, and classifies all known elementary particles. The discovery of the Higgs boson in 2012 confirmed a key prediction of the Standard Model. Despite its success, the Standard Model does not include gravity, and physicists are searching for a more complete theory. Quantum electrodynamics, or QED, is the quantum theory of the electromagnetic force. It describes how light and matter interact through the exchange of photons. QED is one of the most accurate theories in science, with predictions that have been confirmed to extraordinary precision. It's a cornerstone of modern physics and has deepened our understanding of the quantum world. Quantum chromodynamics, or QCD, is the theory that describes the strong nuclear force which binds protons and neutrons together in the nucleus. QCD explains how quarks and gluons interact and why protons and neutrons are stable. The strong force is incredibly powerful but acts only over very short distances. QCD is a vital part of the Standard Model and helps explain the structure of matter. Quantum gravity is an area of research that seeks to unify quantum mechanics with general relativity, Einstein's theory of gravity. While quantum physics describes the very small, and relativity describes the very large, combining them into a single framework remains one of the biggest challenges in physics. Theories like string theory and loop quantum gravity are among the leading candidates, but a complete theory of quantum gravity has yet to be found. Quantum computing harnesses the principles of quantum mechanics to process information in ways that classical computers cannot. By using quantum bits or qubits, which can exist in multiple states at once, quantum computers can solve certain problems much faster than traditional computers. This technology has the potential to revolutionize fields like cryptography, optimization, and drug discovery. Although still in its early stages, quantum computing is advancing rapidly. Quantum cryptography uses the principles of quantum mechanics to create secure communication systems. The most well-known method is quantum key distribution, which allows 2 parties to share a secret key with absolute security. Any attempt to eavesdrop on the communication will disturb the quantum states and be detected. Quantum cryptography promises to make information transmission safer than ever before. Quantum teleportation is a process by which the state of a quantum system can be transmitted from one location to another without physically moving the particle itself. This is achieved using quantum entanglement and classical communication. While it doesn't allow for teleporting people or objects, quantum teleportation is a powerful tool for quantum communication and computing. Quantum sensors use quantum effects to achieve extremely high sensitivity and precision in measuring physical quantities like time, magnetic fields, and gravity. These sensors are already being used in applications such as atomic clocks, medical imaging, and navigation. As quantum technology advances, quantum sensors are expected to play an even bigger role in science and industry. Quantum optics is the study of how light interacts with matter at the quantum level. It explores phenomena like single photon emission, quantum entanglement of light, and the manipulation of quantum states using lasers. Quantum optics has led to advances in communication, computing, and fundamental tests of quantum theory. It's a vibrant field that continues to push the boundaries of what's possible with light. Quantum dots are tiny semiconductor particles that have unique quantum properties. Their size is so small that their electronic characteristics are determined by quantum mechanics. Quantum dots are used in displays, solar cells, and medical imaging because they can emit light in very specific colors. Their tunable properties make them valuable in both research and technology. Quantum biology is an emerging field that investigates whether quantum phenomena play a role in biological processes. Some studies suggest that quantum effects may be involved in photosynthesis, bird navigation, and even our sense of smell. While the field is still young, it offers exciting possibilities for understanding life at the most fundamental level. Quantum materials are substances whose properties are dominated by quantum effects. Examples include superconductors, which conduct electricity with zero resistance, and topological insulators, which have unique surface states. These materials are at the forefront of research and have the potential to revolutionize electronics, energy, and computing. Quantum metrology is the science of making ultra-precise measurements using quantum phenomena. By exploiting properties like entanglement and superposition, scientists can measure time, distance, and other quantities with unprecedented accuracy. Quantum metrology is essential for technologies like GPS, atomic clocks, and advanced scientific experiments. Quantum information theory studies how information is stored, processed, and transmitted using quantum systems. It combines ideas from physics, mathematics, and computer science to develop new ways of encoding and manipulating information. Quantum information theory underpins technologies like quantum computing and quantum communication, and it's a rapidly growing field. Quantum decoherence is the process by which quantum systems lose their quantum properties and behave more classically. This happens when a quantum system interacts with its environment, causing the delicate superpositions to break down. Decoherence is a major challenge in building quantum computers and maintaining quantum states for long periods. Quantum Zeno effect is a phenomenon where frequent observation of a quantum system can prevent it from changing its state. It's named after Zeno's paradoxes, which deal with motion and change. In quantum mechanics, this effect shows how measurement can influence the evolution of a system, sometimes even freezing it in place. Bell's theorem is a fundamental result in quantum physics that shows no local hidden variable theory can reproduce all the predictions of quantum mechanics. Experiments testing Bell's inequalities have confirmed the non-local nature of quantum entanglement. Bell's theorem has deep implications for our understanding of reality and the limits of classical explanations. Quantum physics is full of paradoxes that challenge our intuition. From Schrödinger's cat to the EPR paradox and the measurement problem, these puzzles highlight the strange and sometimes contradictory nature of the quantum world. Exploring these paradoxes helps physicists refine their theories and deepen our understanding of reality. There are many interpretations of quantum mechanics, each offering a different perspective on what the mathematics means. The Copenhagen interpretation is the most widely taught, but others include the many worlds interpretation, pilot wave theory, and objective collapse models. These interpretations attempt to answer questions about measurement, reality, and the role of the observer. Randomness is built into the fabric of quantum mechanics. Unlike classical randomness, which is due to ignorance, quantum randomness is fundamental and unavoidable. When a quantum system is measured, the outcome is genuinely unpredictable, even if you know everything about the system's initial state. This intrinsic randomness is used in quantum random number generators for cryptography. Quantum simulation uses quantum systems to model and study other complex quantum systems that are difficult to simulate with classical computers. This approach is valuable for understanding materials, chemical reactions, and fundamental physics. Quantum simulators are already providing insights into problems that were previously intractable. Quantum thermodynamics studies how the laws of thermodynamics apply to quantum systems. It explores questions like how energy flows and entropy behaves at the quantum level. This field is important for understanding the limits of quantum machines and the fundamental connections between information and energy. Quantum phase transitions occur at absolute zero temperature, where quantum fluctuations drive changes in the state of matter. Unlike classical phase transitions, which are caused by thermal energy, quantum phase transitions are governed by quantum mechanics. These transitions are important for understanding exotic states of matter and have applications in quantum materials research. Quantum physics isn't just theoretical, it has practical applications that impact our daily lives. Technologies like lasers, MRI scanners, and semiconductors all rely on quantum principles. Even the GPS in your phone depends on quantum effects and atomic clocks. As quantum technology advances, we can expect even more innovations to emerge, transforming medicine, communication, and computing. Despite its successes, quantum physics still faces many challenges and unanswered questions. How can we unify quantum mechanics with gravity? What is the true nature of measurement and reality? Can we build large-scale quantum computers? These open questions drive ongoing research and inspire new generations of physicists to explore the quantum frontier. The future of quantum physics is full of promise and excitement. As our understanding deepens, we're likely to see new technologies, materials, and discoveries that will reshape our world. Quantum computing, communication, and sensing are just the beginning. The quest to unlock the mysteries of the quantum realm continues, pushing the boundaries of science and human knowledge. We've covered the core concepts, experiments, and applications of quantum physics, from its mysterious beginnings to its modern-day impact. Quantum physics challenges our understanding of reality and opens up new possibilities for technology and discovery. As we continue to explore the quantum world, we're reminded that the universe is far more complex and fascinating than we ever imagined. Thank you for joining this journey into the quantum realm. Stay curious and keep exploring.